right, guys, let's pick back up in our notes. We are now talking about something called the osteon. And in your notes, you really have this diagram right here, unlabeled, nice and centered in the middle of the paper. And so we're going to label several components of this diagram. And then as you label different parts, I'm going to also tell you a little bit about those parts. So think about this same way with the long bone. We're going to annotate this diagram first by labeling. So our first thing that we're going to label, wait a minute, let's go back. Or the first thing that we're going to identify is this entire structure right here that is a circular column pulled out of the larger bone. This thing, bracket it off and label this as an osteon. An osteon is considered a single unit of bone. And I think that, when we look at these diagrams, they look like columns. And there are multiple osteons. Here's a column, here's an osteon, here's an osteon, here's an osteon, here's another one that are all bunched together to create the overall bone structure. So pull out and label one osteon and then identify it as the smallest unit or the smallest single unit of bone. The next thing that we're going to label is a lamella. And so here is a nice picture of a lamella. A lamella is a ring of bone matrix that actually creates these concentric circles of the osteon. And so here is one lamella, here is another lamella, here is a third lamella ring, and here is a fourth lamella ring. So these layers of the osteon are called lamella. Now within the lamella, there are these little pockets. And so these pockets are called lacunae. Here's the word lacunae. Imagine where each one of these cells, these are all cells, each one of these cells sit. There has to be a little pocket or a divot for the cell to sit in. And so a lacunae is a pocket that exists in between layers or lamella that cells are going to sit in. So there's our last little note there. The matured bone cells, the osteocytes, will sit in these lacunae. If we stick with the same diagram, the next thing we're going to look at are these little tiny, they almost look like cracks in the bones. These are little canals called canaliculi. That's the plural, canaliculi. So these little canals are going to allow for the arms of the osteocytes to branch out. So remember, our matured bone cell, our osteocyte, sort of looks like a fried egg, but then it has all of these branches off of it. Those branches are going to be important and they need a space to exist. So canaliculi are the spaces that allow for the arms of the osteocytes. Now, what's important about this is that it allows osteocytes to connect to neighboring osteocytes. So, for example, this cell way out here is trapped. All of these osteocytes are trapped. That's sort of the definition of an osteocyte. It is a trapped bone cell. And so this osteocyte, because it is trapped, has no access to nutrients. It needs to extend an arm out to the next inner osteocyte, who then extends an arm out to the next inner osteocyte, who then extends an arm into this hollow space right here that we will find is full of these blood vessels. So the cells are trapped way far away for any sort of oxygen, CO2 blood supply exchange source. And so they have to kind of reach out their arms to be able to connect to neighboring osteocytes to stream nutrients. So the canaliculi are really important to allow those osteocytes the opportunity to reach out. Now, the main blood supply exists in this hollow center of an osteon, and that is called a haversian or central canal. And so every single osteon over here, remember osteons are these columns, every single osteon has its own artery in the middle of it. And that artery is going to supply blood flow to the cells that exist in the osteon. So here is an artery coming up the middle of this osteon. Here we see the artery peeking out of this osteon. Here's another artery peeking out of this osteon. There is one central canal or haversian canal per osteon, and inside that canal is a blood vessel. So this is a primary blood supply for that osteon. I do want to address these sort of horizontal connecting channels. So these are called Volkmann's canals. These are horizontal canals that will extend the blood supply between osteons. So the haversian canal is really to supply one osteon, and the Volkmann's canal will extend blood supply between neighboring osteons. So here's a big note, but is worth and is very important. This whole system that I have just described really details, oh my goodness, we do not want to reset, hold on. This whole system that I've just described shows us, details the interconnected nature of an osteon. So think about all of these players are dependent upon each other. So the osteocytes that are trapped are dependent upon their neighboring osteocytes and streaming nutrients from them. And the next inner row is dependent again on them as well. And it all tracks back to the main blood supply that exists in the haversian system or the haversian canal. Okay, the next section of your notes, we're going to talk about bone development. So how did we grow bone in the first place? As an embryo, how did we all of a sudden get some bone? And then we're also going to talk about something called remodeling, which is this constant balance of building up bone and breaking down bone to store up and to release calcium and other salts that are stored in our bones. So development, you have a little section here that is just under the word development and remodeling. Development, remind yourself, this is a conversation about the first time that you're growing a bone as an embryo. Remodeling is about repair to damage bone or growth as an overall organism. Like as you grow in size from an infant to a toddler to a toddler to a kindergartner, and then you just kind of keep growing. That is all part of the process of remodeling. So remodeling, and we'll see this in a second, remodeling is actually the sum of all of the activities that are called deposition and resorption, not reabsorption, but resorption. So deposition, you see the little plus beside it, that is anytime we are building bone and those osteoblasts are called into gear and they begin building bone matrix. Resorption is about breaking the bone down and is directly associated with osteoclast activity. Okay, so your next section of notes, or the next thing that you see in your notes, are these two terms, interstitial and appositional growth. And so I want to make sure that you understand the difference between interstitial and appositional growth. Interstitial growth is when, as an embryo, we grow a bone in length. And so these are typically, this is a term that's typically applied to long bones. And it's due to a surge in hormones. And actually, you can have interstitial growth as an organism as you grow as well. Appositional growth is growth in a bone's thickness or width, the width of a bone. And so here you can see in this diagram, if we took a cross section of a long bone, look at the thickness in the actual long bone in the diaphysis of an infant compared to a child, a young adult. And then as we mature, as we continue into adulthood and even age, that thickness declines again. So it is kind of thin when you are born, and it thickens as you grow. And then you hit a certain point in your life where you kind of stop appositional growth, or it slows down, and your bones become more thin. So here's what you should know about appositional growth. Your bones adjust to stress and mechanical use. So basically, the more that you use your bones, this is working out, exercising, a particular skill or sport, the more that you use your bone, the bigger your muscle becomes attached to that bone, and your bone needs to respond. Your bone wants to strengthen itself to support the muscle. So almost always we see appositional growth attached to muscle mass. How much muscle mass do you have? So if you have a lot of muscle mass, you're going to see increase appositional growth, and your bone will become thicker to support that muscle mass. If for some reason you have a decline in muscle mass, perhaps because you have aged and you are less active, or as this figure is showing us, you have injured a body, a limb in particular, in this case a leg, and it's been in a cast, your muscle, because it's not being used, has atrophied. So if you were to look at, I know you're thinking like, hey, Miss Mac, why are we talking about muscles? This is skeletal. Well, the bone in this leg, because the muscle is smaller, the muscle has atrophied, the bone thickness in this leg is less than the bone thickness in this leg. So now as this person rehabs and begins to use this leg again and rebuilds that muscle mass, their body will respond, their skeletal system will respond by increasing appositional growth in just these two leg bones, the tibia and the fibula, to support the muscle mass that's getting ready to be put back on. The next section, I understand, remember we talked about, I accidentally gave you the notes packet from 2 years ago, I think, in my hurry of copying things before NTI. It didn't have the bone marrow section in it. So the next part of your notes says B, appositional growth types. That is going to be a little bit different. So we're going to talk about embryonic bone development right now. So you can kind of scratch out the appositional growth type, and you can write over top of it embryonic bone development. And this first type of embryonic bone development goes nicely with the diagram that exists on your notes. So what we have talked about right now, or so far, is really a little bit more about remodeling. How do your bones change as you age? Well, they get longer, which was interstitial growth, and they get thicker, which was appositional growth. Now we're going to talk about bone development for the first time ever. So as an embryo, as you are growing, your bones are developing. And so the first type of bone development as an embryo is called endochondral ossification. This is the bone development that occurs in your long bones, your short bones, and your irregular bones. So see my diagram on the side? That would be anything that is blue on the diagram. The bone will, any of those blue bones will develop in this manner that I'm getting ready to detail, called endochondral ossification. Again, that's all of the bones except the skull and the clavicle, or the blue bones here on my diagram. So here's an overview of what happens, but really endochondral ossification is shown on your paper in this figure of numbers progressing 1 through 5 and eventually growing a long bone. But essentially you have parts of a bone that form and then they'll sort of connect together. So in a long bone, we see the diaphysis is going to form first, and then the two epiphyseal ends will form, and then they will kind of grow together. So let's annotate the diagram together. This is what you have in your notes. And we're going to call the first image right here, that is going to be number 1, and it should already be numbered as well. So in number 1, this stage of endochondrial ossification, here's what's happening. Your bone, quote, bone, is mostly made of hyaline cartilage. That's what all the blue represents in this diagram. And so basically the cartilage is going to convert into bone matrix as the bone is growing. And so the first big thing that's going to happen is something called a bone collar forms. And that is right here on the edge of this diagram. So you could label this as a bone collar, and you need to describe step 1 right here as bone collar formation inside the cartilage. Step 2 would be the second picture, and this is showing us that as the bone collar lays down on the side, the cartilage cells right here in the middle, they start to die. And when that happens, the bone collar will release those osteogenic cells that convert into blast cells, and they're going to start laying down bone matrix right here in the middle. And this middle part is now called a primary ossification center. It's the first place that we see actual bone growth and development. Then number 3, our third diagram, you see blood vessels grow into that primary ossification center. So this is called the periosteal bud. And now that you have blood flow, you have a source of nutrients for these cells, these blast cells that have done so much work that they're actually starting to trap themselves in their own matrix that they've created, locking them into place as osteocytes. And so they need some blood flow. They're not going to be able to move towards anything. They need the blood flow to move towards them. So then number 4, our fourth image right here, what we see is the same process really happening again on the ends. And so these are called secondary ossification centers because they develop second. And so they're going to form in the same way, but they're going to form on the epiphyseal ends. And again, periosteal buds will develop into those. And our last stage right here is the idea that our primary ossification center in the middle of the bone and our 2 secondary ossification centers on the ends, they will continue, blast cells will continue to lay down new bone matrix, and they will sort of grow together. And that process still is happening even when you are born and as you mature, even towards puberty. And so we see, because the whole bone started as a piece of cartilage, we see some remnant cartilage. Remember articular cartilage on the ends? Well, there is some of that articular cartilage left over on the proximal and distal epiphyses. And then we see a little bit of cartilage trapped right here in the middle between our primary and secondary ossification centers. Those are our growth plates that will eventually ossify into what is called an epiphyseal plate or an epiphyseal line. So that's how some bones develop. And that's the diagram that you have annotated. Now, the bones that we left out are really flat bones. And so how in the world do flat bones actually grow? That's a shorter conversation. And I know in your notes, you do not even have these words. So you're going to have to kind of squeeze it down here at the bottom. You need the second type of development. It is called intramembranous. So the first type was called endochondrial, which means inside cartilage, right? That's bone growth inside cartilage. This is called intramembranous, which is bone growth inside a membrane. This is how flat bones, which are packed full of spongy tissue, form. All right, now I know you don't have this picture, but we can still talk about the steps. So the first step, step number 1, which we see in this top diagram, you have a whole bunch of stem cells that are going to clump together and create something called an ossification center. Now, it's not terribly important, but if you wanted to know, they're called mesenchymal stem cells. But stem cells are going to clump together. in the middle of this membrane tissue and form an ossification center. Then number 2, very similarly, these stem cells, and that's looking at this diagram right here, these stem cells are going to convert into blast cells, and they're going to start building bone. And as they lay down new matrix, they're going to trap themselves in that matrix. Once they are trapped, they are again called osteocytes, and will need blood vessels to move in and provide some nutrients. So in, oh, wait, hold on. Yeah. So in number 3, which is C, we see that. We see the new bone matrix being formed, and we see the migration of these blood vessels in. And the last thing is that we see the formation of the periosteum around the flat bone. So the periosteal layer is going to form here on the outside. And it's a flat bone, which means it's not very thick. And so the process isn't as involved. And most of our flat bones that are developing through this process really are pretty well done at birth. They don't require a ton more ossification. I mean, some of the bones will, some of the sutures, like in your cranium, will fuse together, but the bones themselves aren't growing a ton. Okay, so that is, I'm sorry it was super confusing because of the incorrect notes packet, but hopefully you may do, and if not, you could go back and rewatch. You essentially needed to add in this last section, this intramembranous ossification section. All right, I will see you all Thursday.